Okay, hi everyone. Welcome to the 61st online Spintronics seminar. It's my great pleasure to introduce our speaker today. Professor Di Wu received his Bachelor's of Science degree in 1997 and a PhD in 2001 in physics from Fudan University in China. After 6 years of postdoc research experience at University of Utah and the University of California, Riverside, he got a faculty position in Nanjing University in 2007, where he is currently a full professor in Department of Physics. His recent research focuses on spin transport in magnetic insulators, and today he will be talking about their recent findings on ultrafast pure spin current generation from an antiferromagnetic insulator. So without further ado, Di, please take it from here.
Okay, thank you. Thank you for the introduction. It's my pleasure to give this talk to present our recent results. My talk includes 4 parts. After the introduction, I will present our experimental observation of ultrafast pure spin current in palladium nickel oxide bilayer. In the third part, I will discuss the physical mechanism of the ultrafast pure spin current generation. The last part is the conclusions. In this part, I will introduce recent progress on the ultrafast pure spin current generation and pure spin current generation from antiferromagnets. There are 2 types of pure spin current. One is the electron type. It can be obtained in conductor. The upspin and downspin move in opposite direction. Therefore, the charge current is 0. There is only a flow of angular momentum. The other one is the spin wave or magnon type. As we know, the spin wave or magnon carries angular momentum. The transport of the magnon is also a flow of angular momentum. Since the transport of spin wave does not need the electron movement, it can occur in magnetic insulator, either ferromagnetic insulator or antiferromagnetic insulator. In this case, the charge current is also 0. In this talk, I will focus on electron type pure spin current. There are many approaches to generate the pure spin current. Here I will introduce 3 mostly used methods. The first one is spin Hall effect. In a non-magnetic metal, a charge current can be converted into a transverse pure spin current via the spin-orbit interaction. This is the most convenient method to generate pure spin current. The second method is spin-Seebeck effect. In a ferromagnetic non-magnetic heterostructure, by applying a temperature gradient, the angular momentum of the magnons can be transferred to the neighboring non-magnetic metal because of the temperature difference between the magnons and electrons. Pure spin current is generated. The third method is spin pumping. When the ferromagnet is in ferromagnetic resonance, the precession of the magnetic moments can produce a pure spin current. Next, I will introduce the ultrafast pure spin current generation by these 3 methods. In this talk, the time scale we are talking about is picosecond or 10⁻12 second. The first example is via the spin Hall effect. In this work, they fabricate a photo switch in the coplanar waveguide. A pulse laser is used to trigger the current. Using this method, a 6 picosecond wide pulse charge current is obtained in the heavy metal layer. Therefore, the ultrafast pure spin current is generated via spin Hall effect. This successfully switches the Coulomb moment by this ultrafast spin current. The second method is via spin-Seebeck effect. A femtosecond pulse laser can induce a picosecond temperature gradient. This red curve is an estimation of temperature gradient. The width of the temperature gradient is less than 5 picoseconds. A pulse spin accumulation in gold is detected using time-resolved Vogue measurements. This spin accumulation is caused by the pure spin current generation by spin Seebeck effect. In this work, instead of measuring the spin accumulation, they measure the terahertz radiation. About 1 picosecond wide radiation is detected. They explain this radiation to the pure spin current generation via spin Seebeck effect. And then the spin current is converted into charge current via inverse spin Hall effect to emit the terahertz radiation. How about spin pumping? As far as I know, there's no successful report using spin pumping. As I introduced before, the spin pumping originates from the FMR. The time scale of the ferromagnetic processing is about 1 nanosecond. 1 picosecond time is not long enough to excite and establish FMR. This could be the reason we don't see the report on this method. The processing of the ferromagnet is relatively slow, but we know the processing of ferromagnet is much faster. It could provide an alternative. Let's look at the antiferromagnetic processing. There are two degenerative processing modes. Both moments process in the same direction. One is counterclockwise processing. The other one is clockwise processing. The processing angle of two magnetic moment sublattices are different because they processing with opposite characters. For the counterclockwise processing, this moment follows right-hand rule. This moment follows the left-hand rule. This will give a weak AC moment. Because of the degeneracy, in general, we cannot observe the phenomena related with the antiferromagnetic processing. In order to lift degeneracy, we need to apply the strong magnetic field. For example, in the spin Seebeck effect, a few Tesla field is needed to observe the spin Seebeck effect. For uniaxial anisotropy antiferromagnet, when the field is perpendicular to the z-axis, the moment gradually tilts toward the field direction. When the field is along the z-axis, a spin flop transition occurs at the large field. You can see a large increase of the spin Seebeck signal around the spin flop field. They found the signal is larger than the signal measured in ferromagnets under similar conditions. They believe the spin Seebeck effect is not fully contributed by spin canting. In this work, they observe a remarkable spin Seebeck signal in palladium chromium oxide bilayer above the spin flop field, about 5 Tesla. They found the magnetic moment, this red curve, and spin Seebeck, this blue curve, this black curve, have different temperature dependence. It means the spin Seebeck effect is not fully contributed by spin canting as well. Very recently, it was demonstrated that spin pumping in antiferromagnets can generate the pure spin current. This is the antiferromagnetic resonance frequency as a function of field. These two curves correspond to two processing modes. This blue curve is beyond the spin flop transition. They fix the frequency of the electromagnetic wave to be 0.24 terahertz. There are two crossing points. One is antiferromagnetic resonance. The other one, they call it quasi-AFMR. They do observe spin pumping signal at these two resonance fields. The resonance fields are more than 2 Tesla and 10 Tesla. Almost at the same time, the other group also observed the spin pumping in antiferromagnets in other material, manganese, fluorine. They also found the spin pumping signal at a few Tesla field. Looking at those works on the pure spin current generation from antiferromagnets, we can see, first, high magnetic field is needed to lift the degeneracy or satisfy the resonance condition. Second, the pure spin current is static. It's not different from the pure spin current generated from ferromagnets. The character of the ultrafast spin dynamics of antiferromagnets does not show up. We are thinking, can we generate pure spin current from antiferromagnets at zero field? This will be good news for applications. Second, can we utilize the ultrafast spin dynamics of antiferromagnets to generate ultrafast pure spin current? The answer is yes. In this part, I will show you our experimental observation of ultrafast pure spin current generation about 1 picosecond wide at zero field and room temperature from the antiferromagnets. We grow our nickel oxide film by pulse laser deposition. This is the read intensity as a function of time. You can see the film can be grown nail by nail on the magnesium oxide 001 surface. We can grow high quality nickel oxide film. In the ultrafast experiments, we grow the film on 111 surface. This is a TEM image. You can clearly see nickel oxide is single crystalline. In the following experiments, I will show you the single crystalline 111 oriented nickel oxide film is the key for our finding. The palladium film is sputtered on nickel oxide. This is our experimental setup. We use a 100 femtosecond linear polarized pulse laser to excite palladium nickel oxide binary. Then we measure the radiation from the sample. All the experiments were done at the room temperature. This is our result. We observe a pulse emission. The pulse width is about 1 picosecond. This is a spectrum of the Fourier transformation. We can see the bandwidth is up to 3 terahertz. I want to emphasize that this experiment is done at zero field and room temperature. First of all, we want to know the origin of the emission. We first measure the emission of the single layer nickel oxide. A weak signal is observed. For comparison, I show you the signal of nickel oxide palladium binary. It's about 80 times larger than the signal of the single layer nickel oxide. That is to say, the observed emission is not the nonlinear optical effects in nickel oxide. The mechanical film is essential for the radiation. Since nickel oxide is magnetic material, we guess this emission is related with spin current. To check whether the emission is a spin current effect, we use a typical method to test. we choose the heavy metal with opposite sign or spin Hall angle. If it's a spin current effect, we should have opposite direction of the charge current. This will change the sign of the emission. Here we choose tungsten and palladium. The spin Hall angle of tungsten is negative. The spin Hall angle of palladium is positive. We also choose copper as a control sample. The spin Hall angle of copper is almost zero. For palladium, the sign of the pulse emission is positive. Once we change the metal into tungsten, the sign of the signal changes to negative. When we choose copper as capping layer, the signal almost disappears. If we zoom in the signal, we can see a very weak signal. This weak signal could be the emission from the nickel oxide film. Once we deposit palladium on top of copper, the signal shows up again, and the sign is the same with palladium. This result also can exclude the possible interfacial optical effects. This is a summary of our results. We can see the sum of the spin Hall angle is directly related with the sum of the pulse amplitude. They always have the same sign. With these results, we conclude our observation is a pure spin current effect. This is our understanding of the mechanism of pulse radiation. The pulse laser excites a pulse pure spin current. The pure spin current is converted into a pure spin charge or a pulse charge current via the inverse spin Hall effect. The pulse charge current emits the pulse radiation. Here we compare the emission intensity of three typical samples: antiferromagnetic nickel oxide, ferromagnetic metal, cobalt iron boron, ferromagnetic insulator, EG. They were measured under similar conditions. The metallic system shows strongest emission. It's about 5 times larger than nickel oxide. The EG film is about 5 times larger than nickel oxide. Although we provide the understanding of the radiation, we still have several unknown questions. First, you might think the quality of our nickel oxide film is poor. There might be some metallic nickel. The source of spin current might be ferromagnetic nickel rather than nickel oxide. Second, the conversion mechanism. Is it converted by the inverse Rashba-Adelstan effect or inverse spin Hall effect? Third, if the source of the spin current is nickel oxide, what is the mechanism? How can we get spin current at the zero field? First of all, we need to judge whether the nickel oxide is antiferromagnetic. We prepare a control sample of permanent nickel oxide bilayer and then field cool from 400 K to low temperature. We found a clear exchange bias effect. The exchange bias disappears at about 400 K. In this work, they measure the Q temperature of nickel oxide. The Q temperature of the film is more than 500 K. It does not change much with reducing the film thickness down to 9 nanometer. We believe the Q temperature of our nickel oxide film should be larger than 400 K. The laser can significantly heat up the sample. We need to estimate the real sample temperature. We estimate the temperature rise by this formula. From all the sample parameters, the temperature rise is estimated to be about 70 K. Therefore, the sample temperature is about 370 K. It's lower than the nickel oxide Q temperature. We should have antiferromagnetic nickel oxide. The radiation is initially demonstrated in metallic system. In this work, they use femtosecond laser to excite iron gold and iron ruthenium bilayers to obtain the pulse radiation. They found the radiation changes sign when the direction of the magnetization is switched. This is a characteristics of the ferromagnetic system. In our sample, the radiation remains almost unchanged while switching the field. It's not sensitive to field. This makes us to believe the spin current is generated from nickel oxide rather than ferromagnetic nickel. In the metallic system, the electrons are excited to be above the Fermi level. The spin-up hot electrons are sp-like character. The effective mass is small. The mobility is fast. The spin-down electrons are d character. The effective mass is large. The mobility is slow. When the hot electron diffuses into the neighboring non-magnetic layer, the spin-up electrons are faster than the spin-down electron. This forms a kind of spin polarized current. It's not pure spin current. In palladium nickel oxide, the density of state is symmetric. The spin current must be pure spin current. In iron silver bismuth, they found the ultrafast spin current can be converted at the interface via the inverse Rashba-Edelstein effect. When the stack order is changed from silver bismuth to bismuth silver, the radiation changes sign. Similar with silver bismuth, is it possible that the spin current is converted at palladium nickel oxide interface? In copper nickel oxide, we don't observe emission. However, with palladium, the emission appears. This means the spin current is not converted at the metal nickel oxide interface. It's converted in palladium via inverse spin Hall effect. The last thing I will discuss is the ultrafast pure spin current generation mechanism. First, we consider the spin Seebeck effect. It was demonstrated in palladium ink. We rule out this possibility by the laser power dependent measurement. This is our measurement result. The amplitude of the emission is proportional to the laser power. In the following slide, I will show you the laser can induce magnons. The magnon numbers are expected to be proportional to the laser power. The temperature gradient is proportional to the laser power. The spin Seebeck effect is a product of the magnon number and the temperature gradient. Therefore, the amplitude should be proportional to the square of power. It disagrees with our observation. We can exclude the spin Seebeck effect. How about spin pumping? For spin pumping, we need high magnetic field and sub-terahertz radiation to meet the resonance condition. In our experiment, we don't apply field and sub-terahertz radiation. The resonance cannot take place. The spin pumping can be excluded. To understand the mechanism, we did experiments on different crystal orientation. Only 111 oriented sample shows strong signal. 100 and 1100 oriented sample don't show signal. Meanwhile, we found only 111 oriented single layer nickel oxide has emission. This gives us an important clue. The crystal symmetry is the key to reveal the mechanism. Since symmetry is important, we fix the direction of the laser polarization, rotate the sample to conduct the measurements. The emission amplitude and even the sign are modulated with a rotating angle. In this figure, we plot the amplitude as a function of angle. You can clearly see there is a period of 120 degrees or threefold symmetry. For comparison, we did the similar measurements on YIG 111. The amplitude for the sine function, the period is 360 degrees, not 120 degrees. It tells us nickel oxide must have different origin from YIG. Since the crystal symmetry is the key point, let's look at the crystal structure of nickel oxide. The nickel atoms form a FCC structure. The magnetic moments are in the 111 plane. It's layered antiferromagnetic. It's ferromagnetic in the 111 plane and antiferromagnetic between 111 planes. To more clearly see the structures, I draw the cross-section of 111 plane. The moment is along 111 latitude direction. The crystal has a threefold symmetry along
It looks like we have some internet issue.
Can you hear me?
I can hear you now. We lost you
Okay.
about a minute ago. Can you repeat what you just said?
Yeah. We try field cooling the sample to change the magnetic state. The sample is field cooled from 400K.
Actually, sorry, can you start from the previous slide? I think we lost you there.
Okay. Yeah. In our case, we don't apply field. It should be multi-domain states. Consider all possible magnetic states or domains. The magnetism is also threefold symmetry. We try field cooling the sample to change the magnetic state. The sample is field cooled from 400K at 9 Tesla field. The field is larger than the spin flop field. We expect to change the distribution of the domain state to study the angular-dependent radiation. As our expectation, the radiation is modulated by the field cooling. The field cooling results further confirm the spin current is related with the magnetism. I want to point out we cannot well control the magnetic domain states by this field cooling. The results after field cooling varies from time to time. We understand our finding from nonlinear optics. According to the nonlinear optics, in a threefold symmetry crystal, when the light propagates along the threefold symmetry axis, the crystal can contribute the angular momentum of 3H bar. For example, in the second harmonic generation process, the annihilation of two right circulopolarized photons can generate one left circulopolarized photon in the threefold symmetry crystal. The energy is clearly conserved. The angular momentum is also conserved in this process. Three photons contribute angular momentum of 3 h-bar. The crystal contributes angular momentum negative 3 h-bar. The total angular momentum is conserved. The SHG can take place. This mechanism was recently applied to antiferromagnetic system. In the antiferromagnets with threefold symmetry, we can excite magnon at zero field by photon. The process is very similar with Raman scattering. In this process, two photons contribute angular momentum of 2 h-bar. The crystal contributes -3 h-bar. The magnon contributes an angular momentum of 1 h-bar. The total angular momentum is conserved. This process can take place. In this paper, they call this mechanism as collinear difference frequency generation, DFG in short. They also did experiments to verify this mechanism. They use laser to excite nickel oxide 111 crystal. They observe period oscillation. The amplitude of the radiation shows 120-degree period, consistent with the DFG theory. We also measure the angular dependent amplitude for our nickel oxide 111 film. We only observe a pulse signal, probably because the damping of our film is much larger than the damping of crystal. The amplitude also shows 120-degree period. We believe our film also follows the DFG mechanism. Finally, we have a preliminary understanding for our finding. The pulse laser can generate magnons or excite magnetic dynamics in nickel oxide 111 film via DFG mechanism. The induced magnons pump pure spin current. This understanding is very preliminary. The detailed excitation process is still not well understood. This is the conclusions. In plating nickel oxide 111 binary, we observe ultrafast pure spin current generation by a pulse laser excitation. This pure spin current is generated from an antiferromagnetic insulator at room temperature and zero field. It can be converted into the broadband terahertz radiation. Finally, I want to thank my collaborators. This work was mainly done by Hong Song and Li Fan. I collaborated this work with Professor Jin's group. I want to thank my colleague, Professor Zhang. Professor Zhao from Fudan University helped us a lot to understand our results. Professor Mi and Professor Qin from Xi'an Jiaotong University performed the TM measurements. Thank you for your attention.
Thank you very much for the interesting talk. Before we go to the Q&A session, can you please go back to slide 34? That's where we lost you.
Yeah.
Can you start from the beginning? I think we lost it at the very beginning of this slide. Can you repeat this slide again?
Okay.
Thank you.
Yeah, since the crystal symmetry is the key point, so let's look at the crystal structure or nickel oxide. The nickel atoms form a FCC structure. The magnetic moments are in the 111 plane. It's a layered antiferromagnetic. It's ferromagnetic in the 111 plane, antiferromagnetic between 111 planes. To more clearly see the structures, I draw the cross-section of the 111 plane. The moment is along 111 -2 direction. You can see the crystal is threefold symmetry along 111 direction. The magnetism is twofold symmetry. But in our case, we don't apply field. It should be multi-domain states. If we consider all possible magnetic states or domains, the magnetism is also threefold symmetry. This is the reason we observe the period of 120 degrees.
Thank you very much for going through this again. This seminar is open for questions. If you have any question, please use the raise hand option from the Zoom, or if you cannot find that, you can always send me a private chat message. And if you're watching us on Twitch, you can type your questions in the chat box and I will read it for you. The first question will be asked by iPhone. Please unmute and go ahead with the question. You need to unmute yourself first. No, okay. If not, we'll go to the second one. For the username with the user ID iPhone, if you cannot, if your microphone is not working, please just send me a text message. I can read your question. We'll go to Ronaldo. Please, Ronaldo, please go ahead with the question.
Hi, thank you for your presentation. I missed the early part of the talk. So what laser energy wavelength did you use? And if you tried different wavelengths?
We only try one wavelength, 800 nanometer.
Okay, thank you.
Dr. Tom Seifert, please go ahead with the question.
Yeah, hi. Thanks a lot for this really nice talk. I had a question to the part where you introduced the mechanism from the Higuchi paper. Could you please go to that slide?
This one?
No, the PRL, where, yeah, this one exactly. So here in the upper graph on the upper left, the previous slide, the 38.
38, okay, yeah.
Yeah, in the upper left graph, you see these strong oscillations, which are probably the 1 terahertz magnon.
Yeah.
Do you understand why you don't see any signature of this in your spin current that makes it to the platinum? In your experiment?
This oscillation is for bulk crystal. For our film, we only see a very tiny peak. We don't see oscillations. So
it's crystal thickness, you would say?
Yeah, I would say crystal thickness or the quality of the sample.
All right, thanks.
I think it's a damping of our film. Maybe it's not very, very large. Yeah.
Okay, the next question, Dr. Yan Chen, please go ahead.
Hi, thanks for the very interesting talk. So from your central result, it seems that on top of the 3-phi signal, there seems to be a small cosine phi component. Yeah, so I was wondering if, what is the physical mechanism underlying this cosine phi component?
You mean this one?
Yes, yes.
Because the sample is a multi-domain state, we don't know the, okay, like this one, there's a it's a multi-domain state. There are, I think, 6 different domains. So we don't know the portion of all the domains. For example, here, if we feel cool, so the distribution of the domain changes, we can get very different patterns.
I see. So I mean, one of the domain is more populated so that we can observe. Okay, I see. Yeah. I see. Okay, thank you.
Kisap Lee, sorry if I butcher your name. Please go ahead with the question.
Okay, thanks for your nice talk. Really, I enjoyed it actually. Also, I understand your excitation laser is not a continuous wave, so your result should be different from the previous Jingxi's group or NK's group for your antiferromagnetic spin pumping method. But when you compare with the cobalt platinum case, for example, which is the ferromagnetic based system, but your case is anti-ferromagnetic system. So actually, my question is following to the this Tom Safer as well. So can you show your spectrum bandwidth? And also, can you compare with your bandwidth between the nickel oxide and cobalt ion boron case?
Okay. Yeah, for the bandwidth, we only found it's up to 3 terahertz. Actually, the absorption of our substrate, magnesium oxide, the limit of the absorption is about 3 terahertz. So we actually we don't know the maximum bandwidth of the nickel oxide.
And in this case, so let's say we have you have like from the 0 to 3 terahertz component, which means your spin current component also cover all these frequency region coming from the nickel oxide. Can I say so? How can I interpret your spectrum?
Excuse me, I don't hear.
Oh, okay, sorry about that. So this spectrum is coming from the terahertz magnum from the nickel oxide?
No. This spectrum actually is a charge current. The pure spin current is converted in platinum, and the charge current emits this terahertz signal.
Oh, okay. Okay, yeah, thank you very much.
So here, so the charge current emits the terahertz signal.
Okay, yeah, thank you.
Dr. Amar Turgut, please, will you go ahead with your question?
Thank you very much for the talk. I mean, there are a lot of mechanisms when you shine the laser on the system. For instance, my former postdoc group, when they did the system for imaging, when they shine the laser on platinum, it creates a thermal gradient. And that thermal gradient generates spin currents, and from the inverse spin Hall effect, you can image the magnetic or antiferromagnetic domains using inverse spin Hall effect. So I'm kind of surprised not to be able to see any thermal effect in your experiments. So I see that it's sensitive to polarization, like at 120 degrees. That's kind of surprising, but I'm surprised not to see any thermal effect, like some part independent of the polarization.
The polarization of the laser or polarization of the magnetism?
Polarization of the lasers.
Oh, here I don't show you the results. Actually, the angular dependent result depends on the laser polarization. Yeah, in our paper we show that results. In this talk, I don't show it. And for the thermal effect, you know, for the antiferromagnetic at zero field, we cannot expect spin Seebeck effect. So we don't think the thermal effect plays in our observation.
mean, in their explanation, the magnons.
Yeah, here is a laser polarization. So
different magnons have degenerate modes, and they have like resulting net non-zero spin current in the platinum. So that was thermal. That was kind of my confusion, but
the thermal magnon from nickel oxide.
yes.
Yeah. Yeah, I agree. There's a very strong temperature gradient, but as I told you, because we don't apply field, so the magnon there's these two degenerate magnon populate a same possibility. So we don't expect any spin feedback from the antiferromagnet.
Okay.
I don't know whether you.
Okay, Emma, we can probably continue discussion after this. I also have some thought on this. Actually, let me read one question from the private chat. It's from Naoto Yamashita. I have a simple question. I'm interested in your experimental method, how to detect terahertz emission from nickel oxide.
How can we detect the emission?
The terahertz emission. Do you have an experimental setup?
Yes, this is we use optical method to detect this emission. We use I remember it's zinc terahertz crystal to measure this terahertz emission. It's a standard method to detect the terahertz emission.
So this is a very similar methods as those other Spintronics terahertz emitters papers using gallium phosphide crystals.
Yeah.
Okay. Yeah. So if you have
similar with the
Yeah, if you can provide a reference, then probably this one, this Nature Nanotechnology paper, it has the detection method in it. Okay, next question. I think Curie, please go ahead with the question.
Yes, thank you for a very interesting talk. So you discussed the role of different antiferromagnetic domains, but what about surface roughness? So my understanding is the magnetic structure of nickel oxide does not break macroscopic time reversal invariance. So in the thermodynamic limit, if the surface is not atomically flat, the effect should disappear. Is that correct?
This is a TMA image. You can see the surface actually is quite rough because this sample is grown on 101 surface. If it's grows on 001 surface, it's much smoother. You can see for this quite rough surface, we still have the effect. So we don't think the roughness is very important for our observation.
Well, how do you explain that there is an effect in the presence of roughness? If you add one atomic layer, your surface spins now point in the opposite direction. So if you average over those two orientations, if they're equally represented, you should get 0, I think.
Yeah, I think this is why this is interesting. Because for the film, the net moment, the net moment is 0, but we still can use the photon to excite magnon. So I don't think the surface plays a very important role in this study. Yeah. Because for example, we try reduce the thickness, we still can observe this effect.
So if you reverse all the spins in the magnetic domain, do you expect the sign of the spin current to change or remain the same?
Yeah, I think it will be easier to discuss for single domain.
Yes,
if it's
let's assume we have a single domain and you reverse all the spins. Should the spin current change sign?
Yeah, I agree. If it's a single domain, if we switch the moment, the sign will switch.
Okay, but then adding one atomic layer at the top is equivalent to switching all the spins in the bulk.
Okay, so you are thinking about there's a domain along the perpendicular to the sample. There's a domain structure.
No. I'm saying there is surface roughness. So what I'm saying is that let's say you have a single antiferromagnetic domain. You can do two things. One thing is you just reverse all the spins everywhere in the bulk.
Yeah.
Okay. The other thing
will change
the other thing you can do is just add one single atomic layer at the top of the surface. What I'm saying is that these two are equivalent for nickel oxide. So if the signal changes sign, if you reverse all the spins in the bulk, it should also reverse if you just add one atomic layer to the top of the surface. But if that's true, then if you average over surface roughness, you should get nothing.
Actually, why do you think if I still don't understand your opinion? Why is it if you add one more atomic layer?
This is the way the magnetic structure in nickel oxide works. So the magnetic structure is invariant with respect to a anti-translation. So that means you reverse all the spins and you shift the crystal by half a magnetic period. Right? So it follows that if you add an atomic layer, it's the same thing as reversing all the spins.
Okay. I understand your point. Yeah.
So maybe you can think about that.
Yeah, I always think about it. I know your point. I know your point. Yeah.
I think this symmetry argument is also related to Emra's question earlier. We can we'll have another informal discussion afterwards as well, so we can get a more in-depth discussion. We have 4 more questions lining up, so let me ask Rolando Aguila.
Yes.
If I put your name again. Yeah.
Don't worry about it. So my question was I forgot what slide it is, but you have this data on nickel oxide with platinum and then the emitted terahertz spectrum.
This one?
Yes. So I think this was somewhat asked before, but my question is, why don't you see any signature of the magnon at 1 terahertz here? So I would expect that there would be less emission at that terahertz, at that 1 terahertz frequency, because the energy is being used into generating the magnon, right? So the magnon is absorbing some of the emitted terahertz. So the question is, why don't you see that effect in the emitted signal?
Yeah, actually, this is a very interesting question. You can say for crystals, they can observe this 1 terahertz magnon. But in our case, we don't see a pulse signal.
No. So, but in your other data, in the other data that you were just showing, right? So you have a huge amount of signal, and it is coming from nickel oxide spin current converted into charge current by the platinum. But in that data, there is no signature at all of the magnon of nickel oxide.
Because this signal actually comes from the nickel oxide. The nickel oxide generates the spin current. So the signal must be related with the nickel oxide dynamics.
Right, but those dynamics are at zero momentum.
Correlate. You say they are correlated. They have very similar shape.
No, well, yes, but I'm more precisely trying to say that the spin dynamics of nickel oxide are the magnetic excitations, and there is a magnon at 1 terahertz for nickel oxide, 1.1 or something like this.
Yeah.
So my question is, why are you not seeing any signature in the emitted terahertz of that one magnon?
So
because you see, in the previous example you show where they have the 1 picosecond oscillation, you know, that's a clear signature of the 1 terahertz magnon. That's an emission signal, right? So that when you photoexcite in some way nickel oxide, it can actually excite that 1 terahertz magnon. You're doing exactly the same, except that the spin current that is generating nickel oxide is being converted into charge current by the platinum. So why is there no signature? Is there something lost in that conversion that loses the signature of the magnon? That's essentially what I'm trying to ask.
But for single layer nickel oxide, there's no transition for the spin current to charge current. This is directly emitted from the nickel oxide film. Because of magnetic dynamics, it emits terahertz signal. Same as this nickel oxide crystal. For the nickel oxide film, we don't observe this 1 terahertz magnon.
Right, but that's an issue of conversion efficiency, right? So you're photoexciting and you detected this tiny signal. That's an issue of how much of the spin current is being, or of the magnetic dynamics is being converted into a free space propagating terahertz pulse. That process is very inefficient if you only have nickel oxide, but the efficiency increases a lot, orders of magnitude, when you convert it into charge current with a platinum.
Right.
So I think somebody asked this earlier on, but why is it that you're not seeing in the platinum converted signal, not on this one that you're showing, in the platinum converted signal, why are you not seeing something similar to this upper left plot? So
if I understand correct, so you are thinking we may still excite 1 terahertz magnon, because we have platinum on top of it, it will enlarge this signal. So we could see this 1 terahertz magnon.
Yes.
Is that correct?
Yes, yes.
So the short answer is we can attribute it to damping is too much large, so we cannot see the 1 terahertz magnon.
So sorry for taking so much time, but one last question: has anybody tried to do this on, like, put platinum layer on a nickel oxide crystal? This would be an easy, not an easy test, but it would be the test, right?
We did that
on a crystal.
Yes.
And you don't see the same signal?
No.
Oh.
Very similar with the film. This is still we are trying to understand.
Okay, thank you.
Welcome.
Those are very interesting questions. We have, let me read one question from chat, then Chong, I will get back to you. This one is from Sriram. Thank you so much for the interesting talk. Is it possible to observe spin pumping in ferromagnet with preferred crystal orientation without any magnetic field?
I don't expect that, because for spin pumping, we must apply a very strong magnetic field to to obtain the resonance. So without field, I don't think so. One possibility, if you look at this, you can see for antiferromagnetic resonance, at this point, oh, no, at this point, the field is zero. Probably, if you can tune the frequency, you might have a resonance with very small field.
Thank you. And Dr. Chong B, please go ahead with your question.
Very nice talk. Following the question she just read, so for the text radiation, my question is why the text radiation have to focus on the direction of laser direction, original laser direction? In other words, should we detect the text radiation everywhere around the sample?
Yeah, we use a detector.
So detector can put everywhere around the sample. You got the same signal.
Oh, yeah. The radiation is all around the space, so it emits from the sample. So it's not directional.
Okay.
The sample behave as a little antenna, and in front of that, there's a collector, there's a lens to focus that onto a detector.
Yeah.
Okay. Thank you.
I'm gonna read another question from chat, from Rahul Gupta. My question is, what is the effect of magnon-magnon scattering in nickel oxide, if there is? And he has another question also, what is the role of nickel oxide thickness in the terahertz emission?
I answer the second question first. Sure. We reduce the thickness, we still can observe the signal. For example, I remember with this experiment on 10 nanometer, we still can get the signal. So it's not very sensitive to the thickness. For the first question about the magnon scattering, actually we don't consider this in our explanation. So frankly, I would say I don't know that. Yeah.
Okay, yeah, thank you very much. Do you have any other question? I think I read all the questions in chat as well. Let me check on Twitch. Nope, I think we exhausted all the questions. Thank you very much for this very interesting talk, very interesting discussion.